In this video, we just wanted to share a few more mathematical ideas about polynomials. We considered talking about the fact that polynomials form a ring. So you can think about polynomials as mathematical objects themselves, and then you can think about the identities 0 and 1. You can think about closure under addition and multiplication, how when you put these polynomials together, you still get another polynomial. Then the associative properties, distributive property, all the stuff that goes into being a ring. And this is important, especially the idea of students taking something that is a process and turning it into an object where they can think about it as a mathematical object. So a polynomial being this process where you put in an x value and you square it, then you multiply it, then you add it, and you do this process to get something out. Shifting their thinking so that students can see polynomials as mathematical objects with properties and you can operate on them together. That's a big shift, and actually there are lots of those shifts in mathematics that are important to take something that's a process and then reify it or put it together into a package where you see it as an object. That's important, but we decided not to focus on that because in the next unit on number systems, we're actually going to deal somewhat with those ideas of structure. So instead, we're just going to say a little bit about the fundamental theorem of algebra. The fundamental theorem can be phrased in different ways, but basically it says that for all non-constant polynomials in one variable, there exists at least one complex root. And we have to exclude constant polynomials because like 7, 12, negative 100, those obviously don't have a root, but the non-constant polynomials all have at least one complex root. Most often we're dealing with polynomials with real coefficients, but we can't guarantee a root in the real numbers. We have to go to the complex numbers to be able to guarantee a root. And that's because of polynomials like this one, where if we wanted to try to look for a root, we're not going to find it in the real numbers, but it's no problem in the complex numbers. So overall, this shift to having to go to the complex numbers is indicating that the real numbers are not algebraically closed, but the complex numbers are algebraically closed. And algebraically closed just informally means that any polynomial equation you can come up with is solvable within your set of numbers that you're working with. The equation x squared plus 1 equals 0 is very easy to express with real numbers, but you can't solve it unless you go to complex numbers, and there's of course many other examples. A little bit of history about the theorem. So the truth of the theorem was asserted and it was believed to be true since the 1600s, but there wasn't a proof of the theorem yet. Then proofs were attempted throughout the 1700s and onward by people like D'Alembert, Euler, Lagrange, and Laplace, but all of their proofs were either incomplete or they contained substantial gaps. Then came Gauss, and a lot of people consider Gauss to be the first one to prove the fundamental theorem of algebra. He actually had several proofs, and there's a saying that you should never trust a person with more than one proof, because if their first proof was valid and sound, they wouldn't have looked for the second proof, and if their second proof was valid and sound, they would have given up the first proof. So Gauss had multiple proofs, and it does turn out later on that people found that Gauss had some implicit gaps in his reasoning as well. Those gaps were later filled, so Gauss's arguments still kind of worked, but they weren't complete. Argand actually published the first complete valid proof in 1806, and it was used by Cauchy in a textbook in 1821, though Cauchy did not actually give a citation to Argand. So in 1806, though, we do have a proof. And then later in the 1900s, Weierstrass gave a different proof of the theorem. The fundamental theorem of algebra leads to another result that is very common in school mathematics, and that is the proposition that every polynomial of degree n has n not necessarily distinct roots. If you're in the complex numbers, you have n roots. If you're in strictly the real numbers, then you have at most n roots. But this statement sometimes is called the fundamental theorem of algebra, but to be clear, it's not actually the fundamental theorem of algebra. It's a consequence of the fundamental theorem of algebra. And you can sort of see how that might follow. If you imagine a polynomial, then the fundamental theorem of algebra gives you one root. Then you can factor out that root and you're left with a smaller degree polynomial. With that smaller degree polynomial, you can factor out another root because of the fundamental theorem of algebra. And so then you can just continue decreasing your degree until you're all the way down. So that application, repeated application of the fundamental theorem of algebra gives you these set of roots. And so you can take that set of roots and then think of that in terms of this proposition. Another useful way to think about this is that you can rewrite every non-constant polynomial in one variable. You can rewrite it as the product of linear factors. And this is, I think, the most useful way in terms of high school mathematics. This is the most useful way to kind of think about it because it allows you to break down polynomials. Many students have a pretty restricted view of polynomials where they think that it has to be x raised to various powers with coefficients in front of it and all added together. Students will think that if there's any parentheses involved that that's not quite right. They'll think they have to expand out and get rid of those parentheses before they can work with their polynomial. But actually, as you know, the parentheses can be very helpful. They can reveal the structure of the polynomial, things that are happening. And also, thinking about building up a polynomial with linear factors, it's very helpful to build it up from the roots and to keep things grouped in that way so that you can see the roots and see what's happening. So for example, you can build a polynomial to do exactly what you want it to do. You can have it go through specified roots. You could have it go through, or you could have it bounce off of roots if you use multiplicities. You can also use the leading coefficient to stretch it or shrink it or to flip it. So you can sort of feel like you're now exerting control over polynomials and feel like you have this real good grasp of how to work with them. And as we saw in the math tasks for the polynomials, you can not only make polynomials that go through zeros, but you can also use those zeros to then move the polynomial and have it go through other special points. So this idea of that grows from the fundamental theorem of algebra, which is that you can build a polynomial from its linear factors, is similar to the idea of building up natural numbers from their prime factors. So in a sense, the fundamental theorem of arithmetic, which gives you a way to break down natural numbers into their primes, it's analogous, loosely analogous, to the fundamental theorem of algebra, which has this consequence of revealing the building blocks of polynomials. So in a sense, it's like the building blocks of number and the building blocks of polynomials. Those are kind of the objects of study in arithmetic and the objects of study in algebra.